In the previous lecture, we have discussed about element approach in the flexibility matrix method. The basic formulation of the flexibility matrix, the structure flexibility matrix delta, and the displacement vector delta L due to externally applied loads at the structure coordinates. They can be formulated in a systematic way in the element approach. So what we do there is we divide the structure into certain elements, and we first of all formulate the force transformation matrix, which is this F matrix. That is essentially a connection between the element forces and the structure forces, defined as R star, which represents a vector of element forces, is equal to the force transformation matrix into the structure forces R. More precisely, this R star contains forces corresponding to element coordinates like 1 star, 2 star in this typical element, or in this example I have given the element coordinates over here. So the forces corresponding to these coordinates 1 star, 2 star, 3 star and 4 star will be the elements of this vector, and the elements of this vector would be the forces corresponding to the structure coordinates, that is 1 and 2 in this case, in this example. So to develop, say, the first column of this F matrix, we are going to set the first structure force or R1 to 1 and the other structure forces R2 to all other forces to 0, and find out the element forces. So the element forces then, say R1 to say Rm for example, they would represent the coefficients in the first column of the F matrix. Well, delta star matrix represents the structure, this is the element, star represents element flexibility matrix, which is unassembled element flexibility matrix. Right. Now for illustration, I have taken an example of a continuous beam over here. Now before going to that, let us again recollect what is the element flexibility matrix of a typical beam element as given over here. So this is a typical beam element having coordinates 1 star and 2 star, which represent essentially the moment at this end and moment at the other end. Now the displacements corresponding to these two coordinates are essentially the components of this matrix. So delta star is equal to, if you give a moment of unity at this end, the displacement produced, or rather the rotation produced at this end would be equal to L divided by 3EI, which is derived in one of the previous lectures, and that is equal to, say, 2 into L divided by 6EI, that is nothing but L divided by 3EI. The rotation produced at the other end will be minus L divided by 6EI, that is given as this term, and displacement produced when, or rotation produced when we apply a unit rotation at the other end would be given by minus L divided by 6EI and plus L divided by 3EI. So they are the components of this particular matrix. To be more precise, to develop the first column of this, we can put the moment corresponding to this coordinate equal to 1 and find out the rotations corresponding to 1 star and 2 star. They are the elements of the first column. Elements of second column could be developed by putting the moment corresponding to this 2 star equal to 1 and the rotations corresponding to 1 star and 2 star are the elements of this column, second column. Right. Now let us come back to this example continuous beam example. First of all, I have found out the degree of static indeterminacy of the structure, that is equal to 2, as we have seen this example previously for the structure approach. Now, this is the structure coordinates of this particular example. We have a moment coordinate over here, we have a moment coordinate over there. So, if you remove the moment from here and the moment from there, the structure will become statically determinate. This span and this span then will behave like simply supported spans. Now, I have identified the elements of this structure as, say, AB as one element and BC as the second element. Let me call AB as element number 1, BC as element number 2. And the element coordinates are respectively 1 star, 2 star for element 1 and 3 star and 4 star for element number 2. Now, let us develop the force transformation matrix. So, the force transformation matrix for this case would be developed in the following manner. Let us put first of all the force R1 corresponding to the first structure coordinate equal to 1 and force R2 is equal to 0, or the moment here is equal to 1 and the moment here is equal to 0. In that case, the moment corresponding to the element coordinates would be the first column of the F matrix. So when this is equal to 1, the moment corresponding to 1 star would be 1. The moment corresponding to 2 star, 3 star and 4 star would be 0 because the moment corresponding to 2 is 0 over here. There is a 0 here, 0 corresponding to 3 star and 0 corresponding to 4 star. Second column of this matrix, this is the first column. Second column will be developed by setting R2 is equal to 1 and R1 is equal to 0. So when we put the second force in the structure equal to 1, say R2 is equal to 1 and R1 is equal to 0, this force or moment will become 0. This moment, the moment corresponding to 2 star will become plus 1. The moment corresponding to 3 star will become minus 1 because the moment here is 1 and the moment in this span would be opposite to that. So, moment corresponding to 3 star in the element coordinate system would be minus 1 and the moment corresponding to 4 star would be 0. If I write that over here, we have a 0 here, a plus 1, a minus 1 and 0. So, that is the force transformation matrix. Now, delta star, which is the unassembled element flexibility matrix for all the elements in the structure. Delta star is equal to the element flexibility matrix for the first element would be, let us put 1 by 6 EI outside. Well, EI for this structure is a constant. Now within brackets we have 2 into L. L for the first span is 3 meters. So 2 into L is 6, minus 1 there, minus 3. This is minus 3 and this is 6. So this is following this typical beam element and the flexibility matrix for that. Now that is the flexibility matrix for the first element. Now the flexibility matrix for the second element is going to be added as the next diagonal, or rather the matrix is going to be a tri-diagonal matrix finally. Let us draw a line here and draw a line here and write the flexibility matrix corresponding to the second element. In this part we are going to have zeros and this part we are going to have zeros. Okay. Now L by 3EI for corresponding to 3 would be, well, the span is equal to 4 meters in length. So this number is going to be 8, so that the number over there would be 8 divided by 6ei, that is 4 divided by 3ei, L divided by 3, that is fine. So this term would be minus 4, this term would be minus 4, and this term would be 8, following again that matrix. So this is the element, unassembled element flexibility matrix. These terms are zeros. To have more clarity over here, the element flexibility matrix is defined as, say, delta star, the displacements corresponding to the element coordinates, is equal to the element flexibility matrix small delta star into the element forces, let us say R star. So delta star will contain 4 terms. In this case, corresponding to 1 star, 2 star, 3 star and 4 star, there are 4 terms in the delta star vector. R star also will contain 4 terms, R1, R2, R3, R4 with stars. So delta, this matrix will be containing 4 by 4 as its size, 4 by 4 number of elements. So that is the matrix which is covered over here, given over here. Now further, we have the force transformation matrix and the element flexibility matrix available. Now we can find out the delta matrix and delta L vector straight away through calculation. So if you do this, delta is equal to F transpose delta star into F, we are going to get well, we know that transpose of this matrix would be just interchanging the rows and columns. So the matrix multiplication, transpose, matrix multiplication are not being covered in detail in these lectures. It is presumed that a person who is attending this course has a minimal knowledge of matrix operations, matrix multiplication, transpose of a matrix, what is a symmetric matrix and things like that. Now, the final form of delta would be 1 by 6 Ci (6 minus 3 and 14). We may compare this flexibility matrix with what is obtained earlier in the previous lecture for the same problem solved by the structured approach or system approach. Now similarly, if we calculate this delta L vector using this relation, well, before that we require the P prime. I forgot the P star vector. Okay, let us develop the P star vector. P star vector contains equivalent joint loads. So P star vector corresponding to the element coordinates 1 star, 2 star, 3 star and 4 star are nothing but the restraining forces at these supports applied in a reverse fashion. If you find out the fixed moments due to the externally applied forces at these two ends of this span, you are going to get, we have already derived the fixed moments due to a UDL acting in a span throughout in one of the previous lectures. So the number here would be if it is W per meter, the fixed moment here, of course, span is L. We have E, I as the properties. This is W L square by 12. This moment is also equal to W L square by 12. We follow that. And for a point load, say eccentric point load, capital W with this is A and this is B. This moment is equal to W A B square divided by A plus B the whole square, or if A plus B is equal to L, we have L square. This moment is equal to W B A square divided by L square, where L is equal to A plus B. So we follow that over here. Now, due to this load 5 kN per meter, we have 5 into 3 square divided by 12 as anti-clockwise on this end, and on the other end we have clockwise 5 into 3 square divided by 12. If you apply those forces in the reverse fashion, in the same span, we are going to get the equivalent joint loads. The equivalent joint loads are nothing but the joint loads which can produce the same bending moment and shear force as in the case of the externally applied forces. The forces which can produce the same bending moment as the externally applied forces can be called as the equivalent joint loads. So P star will contain equivalent joint loads, and once again they are nothing but the restraining forces applied in a reverse direction. So P star would contain 3.75. The moment which was anti-clockwise here is applied clockwise, and moment which is clockwise at the other is applied as anti-clockwise, minus 3.75. For this span, 5 and minus 5. Following these relations. Now, if you do this, delta L is equal to F transpose delta star P star, we are going to get is equal to 1/6 EI (33.75) here, and minus 93.75. Solution of this is already given in the previous lecture, but for completeness I am going to give the final solution. We are going to solve the equation delta L plus delta multiplied by the redundant forces is equal to the total displacements corresponding to the structure coordinates. We have delta L here, delta available over here, R is the unknown forces, and this delta will contain zeros because there is no support segment. If you solve that, we are going to get R vector as minus 2.55 and 6.1. And once you have the values of R, we can now find out the bending moment everywhere and draw the bending moment diagram. The BMD would look like this. This is 2.55. This is 6.15. Connect them. Over that, we are going to superimpose simply supported bending moment diagram. This is 5.625. Of course, the ordinate is equal to W L square by 8 for UDL. And here, this number is 4. The BMD is the disjoint portion. We have bending moment given in kilonewton meter. That is a simple illustration of the element approach to the flexibility matrix method, and that is the end of this session.